Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video, well, we're going to take a look at a case study. We're going to take a look at a process capability improvement case study, and the case study is going to be using this simple principle: inputs control outputs. The more control you put here, and I mean fixing things. Yeah, so a control is just stopping variables moving, stopping operators adjusting, stopping materials from being poor quality when they come in, fixing the variables over this side, and then you can please the customer, get the quality results over the other side, and of course your process makes money. So we're going to take a look at a case study. There's going to be two of these, so there's going to be two videos. Look out for both of them. Just before we get into the case study, just a little reminder, please leave some comments below this video. Please also click the like, as it helps with the channel. If you'd like to know more about any of the concepts that we cover in this video, well, don't forget, drink tea, read the paper. My latest book covers everything that's in this video and much more besides. So please do that if you're interested in knowing something a little bit more. So let's get into this case study. Okay, so here we are. It's there's a very simple project title here, Stage 2 Rework, but actually the process is it's a welding process. Okay, so what you're going to see, they're making some assembly, and then the assembly's and it's an automatic welder. So there's a robot, the operator's feeding the materials in, and the robot does all the work. Okay, and what you're seeing is that the ultimate product is a reject. Ultimately, it's rework, and they have to then manually correct the problem. So currently, look, rework. So here's the define side of things, but rework is causing 15% downtime at a cost of £800 per shift. Yeah, so this is a really expensive problem if you just leave it running in the process, and they like to get the 15% down to 3%. And then get the cost per shift down to £160, saving £640 a day. So there's the sort of very simple define part of the project. Okay, let's do a little bit of measurement. So here's the current problem. So you can see they call these stud failures. This is a period over 2 weeks, and you can see they're pretty much hitting around about sort of 75-80 a day of these failures on this automatic welding process. Now you're going to see this in other case studies. This is a standard way of getting a process under control. You can either get a process under control by using the FMEA, and you can do this before you go live with the process, or what you can do is you can implement the process in a very half-assed way, create a problem. When the problem gets painful enough, then of course what you do is you come back and you use process flow, and the process flow diagram is then used, and this is just describing the process there, but the process flow diagram is then used to populate the cause and effect diagram. So we're going process flow, cause and effect, because they've implemented chaos in their process. They didn't put these controls in place beforehand. So of course the flow diagram, now what's it for? Well, we're simply going to visit every box on this diagram and ask ourselves, what are the variables in this stage? In step 1, what are the variables in step 1? What are the variables in step 2? What are the variables in step 3? So it's each box you're just going to say, okay, what are the critical variables that contribute to my welding problem, to my rework problem? And as I said earlier, there's a few photos, look, of the process working. Here are the finished products. So there they are with the studs welding on these bars, and there's various stages where the bars are welded on, the bars are also bent to shape. So it's a fairly complex sort of automated welding and bending process that they've got. But the issue is that the welds are simply falling off, the studs are falling off. And there's the product. It's something that goes in concrete floor, so you can see the studs here. These are what's being welded on, and they go in a concrete floor, and it's an expansion. It's an expansion joint of some description. So once they've gone process flow, cause and effect. Now what are they doing here? Well, of course, what they're doing is they're trying to replicate this picture right here. So what we've got is a cause and effect diagram. All the items on the cause and effect diagram are inputs to the process. Really important. What the cause and effect diagram is about is just identifying all the inputs, and it's important all of them are on there. Whether we think they're a problem or not, all of the inputs are on the cause and effect diagram. So this diagram is identifying inputs. And then what they do is they decide whether the input is controlled or not. And the N here against a variable means that it's not controlled. Okay, so they don't have any standard, they don't have any agreed way of managing that particular variable. So you can see there is not a single C. Now, by the way, if the variable was under control, so we'll take bowl feeder settings, what would be next to bowl feeder settings? If they were under control, a C would be next to them. But there isn't any. Every single variable is an N. They've implemented complete chaos into this manufacturing system, and consequently the process doesn't work very well. So what they're going to do now is they're going to show us how they stepped through the variables that they identified to control. Now, they're not going to control all of these, but they're going to control probably, I think, in the end of the project, about 60% of them. And they're starting here, look, with the stacking of the material. So one of the problems that the operator noticed is that the material is not in good shape. So let's go through what they've decided to control. So now they have a stacking procedure. Now it's a very simple thing really, because what you've got is long bars of metal. They're on a pallet and they're all stacked up, so it's a really heavy weight that you're storing. And one of the things that they keep doing is they store it just sitting on two beams in the warehouse. And what happens? Well, the material takes a bend because of the weight of the material that they're handling. And this very simple standard operating procedure basically says, guys, we need to control it in the middle as well. So they've agreed a standard. So now they've agreed a standard, written it down. Now they can audit it and control it. Okay, moving on. What else have you got? So the improvement in the handovers. So they weren't communicating shift to shift. So I think they just put a simple logbook. That's quite a common thing, but it wasn't in place. Although it seems like a common, sensible thing, that wasn't in place. What else did they move on to? Now they've moved over here, look, to the condition of the strip. Oily, rusty, bent. Well, of course, by the very nature of controlling that thing up there, they've probably dealt with the bent strip. Now this is incoming material though that's in these conditions, and I believe what they've done is they've now color coded. They've color coded the material. so that because they've got 3 suppliers. And now of course what they can do is they can control the quality of the material from the individual suppliers. So if they do get a problem, they'll see what the color of the material is, they'll be able to feed that back to the supplier, and then we can deal with that. But of course what they've done now, of course, is they've given out standards. They've come up with standard operating procedure for the suppliers, and now they're controlling that. They know which material belongs to who. What else is going on here? Now we start getting into some of the equipment settings. So we're over here now, look. And by the way, just a reminder, none of this is complicated. None of these things are individually difficult to do, but collectively they make a very complex problem. But what do? You break it into inputs. You simply break it into a diagram like this, and you look at each individual input, and each individual solution is simple. Improving your process capability is really, really simple if you have the discipline and the detail to go through every variable individually and fix it, come up with a standard way of eliminating the variability. Your process will behave itself. So let's carry on and look at what they're doing on the cause and effect diagram. So here we are, look. Now they're looking at the machine, as I mentioned earlier. So now they're looking at electrode change, gripper change, and changing over the product type. And you see them now writing standard operating procedures. This is for the electrode changeover. What else have we got? This is a standard operating procedure for the gripper changeover. So they're coming up with standard ways of doing simple maintenance, setting up of the machine, etc. Replacing of the stud gun is another one. Okay, so again, standard operating procedure, standard way of doing this. Identify the variable, control the variable, and see what happens to the process. Moving on. Now they've got a problem with another supplier. So the studs come in pre-made, and they're supposed to have a flux ball sitting on the end of the stud for the welding process to work. Some of the flux balls are missing. So of course that's going to get fed back to the supplier. That needs to be sorted out. Now of course previously, in all the chaos that was going on, they didn't know that this was happening. They didn't have time to even discover this because there was so much rework to be done. All they could do was fix it. They couldn't go back and do something proactive. So now we've identified the fact that the flux ball is a problem. Okay, now then, now we're starting to get these SOPs, all right? Now we can go back and look at training. You see, we can do great training now that we have good SOPs. People often say that we're going to train the operators. Well, what are you going to train the operators in? If you haven't come up with standard ways of doing work, there is nothing to train them in. You're just passing on the skill that Johnny has got. That's a poor way to train anybody. Now you can train them in standard operating procedures. And you can see, look, I understand, look, what have they asked them to do? I understand I must work to the standard operating procedures at all times. So there's no skill here. They're saying there's a standard operating procedure for this variable. Your role and responsibility is to stick to it, and that's it. There's nothing else for you to do but to work to the standard operating procedure. So they've identified the SOPs, then they can do training, then they can identify roles and responsibilities. Now this is detailed stuff, but by the way, step by step by step, it's all simple. This is easy. This is really easy if you've got the discipline to do what these guys are doing. So back to the training sign-off sheet. we've got the standard operating procedures. Now we've got a standard way of making sure that everybody's trained, standard way so that they understand what their roles and responsibilities are. Let's move on. Okay, bowl feeder settings. So now we're setting things on the machine. One of the things they're saying here, look, I've told the operators these settings are not to be changed. Absolutely crucial. That's what process control actually means. So let's just think about what they're doing. This is what process control actually means. The operators are not allowed to change the settings. Let's think of it very simply. Look, you have a process. Choose a pen that works. You have a process. You have variable 1 coming into the process, and you have variable 2, which is a setting on the machine. So I'm just going to call this maybe time in this case. Okay, it doesn't matter what it is to make this point. And what you're saying is variable 1 is coming in with lots of different results. So and what's happening, of course, is out here we're getting lots of variability, and maybe we're making defects. So because variable 1 is moving, what we'll do is we'll allow somebody to move variable 2 to fix it. Well, think about the illogical thing you're saying. I have variability here, so I'll fix it with variability here. So now the time, which would be constant if you just set it and took your hand away, time is no longer constant. Time is being moved up and down now by the operator to try and deal with this. Well, now you have 2 variables moving. What will that result in? Well, it can only result in more variation on the output. It's the laws of physics. You've got 2 variables now instead of 1. This is not process control. This is man-made That's man-made chaos. You're shooting yourself in the foot by allowing operators to move variables. Now what they're doing is to say, now, we're going to fix this. And if this is the problem, we'll go and fix this. But we won't solve it by moving 2 variables. That just makes it twice as worse. So let's go back to the case study and see what else they got up to. So they're fixing the settings in the bowl feeder. Now they found that unfortunately they couldn't fix them to the same settings. In theory, they are the same bowl feeder. But a little bit of common sense here says that if that's not true, if they're not the same, use your common sense. Don't stick with common settings if they don't work. So, bit of common sense says one has to be at 56, one has to be at 66. This is probably down to the age of the bowl feeder, etc. But they've put them at standard settings and told the operators you're not to change them. Moving on. Then we've got the welder settings. Here again, look, what are they saying to the operators? You set them and you do not change them. We will shoot you if you change them, because this is true process control. Identify a standard, fix it. And of course with settings, there can be no variability, because once you've hit that dial and you've said that the current should be at 530 amps, it won't move providing you take your hands away and leave it alone. Then there's an hourly check sheet. So this is to make sure that the operator is actually following those procedures. And something that they've done, which is a great little piece of advice, they get the operator to write the number. So the operator has physically got to write 530 amps or whatever the setting is. It isn't a tick sheet. because if you ask him to tick it, if you question him about it, he will say, I was ticking it because it was operating okay. Now that's not the reason why you do the check. You do the check to make sure you're on the standard, not to tick that it's working okay. So collecting real numbers, if you tell somebody that the temperature's got to be 30, the time has got to be 5 seconds, and the ampage has got to be 530, get them to write those numbers down, and they will always adhere to them in that case. They won't want to move off those standards. It's a nice psychological way of keeping your operators honest. Then we've got a little troubleshooting flow diagram. This is really good, so that what you don't get is, again, operators taking it onto their own shoulders to fix a problem. So here, what do? They just check the standard operating procedures. So they're just going through, and in each case, they're checking that the variable has been set up to the rules, because that's their role and responsibility. If everything is set to the rules and the machine's not working properly, then what do? You call for help. You do not try to fix it yourself. Okay, so that's really, really important. Now, something else they delved into, so they're getting really detailed here. They started to look at the 3 suppliers and say, well, I wonder if the 3 suppliers are giving metal that's got the same compounds in the metallic structure. So now they're doing some steel test certificates to make sure that that's okay. So all the suppliers adhering to what they've been asked for. And once they did all of those things, what happened to the process? Well, it can't help itself. It has to get better, because when you control the inputs, you will control the outputs. And there you can see the process capability has been improved from approximately 70 defects per day down to about, what would it be? It's difficult to see on that scale, but it's around about 17, I would say, on average. So a dramatic improvement in the process. Not perfect, and I think they agree that it's not perfect, but they've put enough work in. The problem no longer hurts them. The pain is no longer so difficult to deal with. The process works so much better and is so much more reliable, and they feel that probably that's as good as they want to get. And there's a close-up. There's a close-up of where they are. I mean, those failures look a little bit better than 17 actually. It's probably nearer. Yeah, it's probably nearer 10, isn't it? So fantastic job, well done. Can't remember what the aim was at the beginning, but I think that's pretty much. I think they said 3%. They wanted to get it down to 3% from 15%, and I think that's a lot inside 3%, as it turns out. So at the start of the project, everything was red, everything was out of control. At the end of the project, look, well, they haven't fixed everything, but look at the work they've done. They've done a great job here, getting hold of lots of simple variables. Every one of them was simple, but you have to be disciplined to do this. This is what the best companies do. This is how to make a process behave itself and improve the process capability. And they actually got it down to 2%. Look, so there's the summary. So they managed to get the rework down to 2%, so better than they expected. And then, of course, some of the controls they've put in place is to maintain the gain. And as they mention here, they'll continue working with suppliers and operators, improving the material and any other SLPs, etc., that they need to. And of course, what are they saying? Once you've got these things fixed, what can you do? Well, you can drink tea, you can read the newspaper, and you can count the cash. And that is a great case study. Okay, hope you enjoyed that. I'm going to make the point again. Whether you think that's a simple problem or not, whether you think that's a simple process and it's not like your problem, it doesn't matter. What would your problem look like? It'd look like this picture, but longer. You just have more variables. But what would we do? Well, they've got about 40 variables. They fixed about 30 of them. Yeah, your process might look like 140 variables. What's each one going to look like? Well, they're going to look like settings and maintenance routines and setup procedures and things like that. They're going to look exactly the same. Just be a longer list of simple things. That's the point about this technique. It doesn't matter how complicated your process is or how simple your process is. Inputs control the outputs. And what should you do? Well, you should identify the inputs, and as much as you reasonably can, you should fix them with standard operating procedures, rules. And then you use ISO 9000. What does it do? Well, if you use your ISO 9000 correctly, you audit the SOPs that make money. And then ISO 9000 doesn't just put a certificate on the wall. What does it do? It makes money, because it's supposed to make money. Now that is case study 1. Hope you enjoyed it. In the next video, we'll take a look at exactly this diagram again. We'll take a look at another company with a different process doing exactly the same thing in case study 2. Take a look at it.